Hello and welcome to Toddcast number 16. We're going to continue on acid-base review. This time we're going to move away from just pure unadulterated G-Chem review like the previous Toddcast and get more into applications to organic reactions. And going to discover that learning how to look at an acid-base reaction, literally the reaction of plus with minus, will actually pay incredible dividends for OChem reactions. So this will be the first of many types of OChem reactions you'll see. So let's see how it goes. So want to do a little bit of review to get into it. So picking up what we were saying last time, for the acid, if we want to consider this from an acid perspective, HA, a weak acid, interacts with water. When it does, you get H0 plus and A minus. I'm calling it a weak acid. Reality is this is true for any acid, but generally we use HX for strong, HA for weak. And for organic chemistry, our acids are weak. We just don't deal with any particular strong acids as an organic reagent. We use them as a reactant to help organic molecules do what they need to do. But by and large, if we're talking about organic molecules, they will be weak acids. So the Ka again is H0 plus times A minus, the two products, divided by HA, the reactant, ignoring water because pure liquids, i.e. solvents, do not end up in the equilibrium expression. Okay, we also can look at, let's say, HB, a different acid. So it does the same thing. It reacts with water to form H0 plus and B minus, so it has the same relationship. And so what we're going to do is we're going to compare the strength of these two acids. So last time we mentioned the greater the Ka, the more acidic the compound. That also means the lower the pK, the more acidic the compound is. We're going to take advantage of that relationship. And so a lot of times we're going to have HA reacting with, let's say, B minus, or an HB reacting with an A minus. We want to see how that's going to work. So what's just happened is I flipped around this reaction. So instead of being HB plus H2O going to H0 plus and H or B minus, I now have the reverse reaction. So it's now 1 over Ka, because Ka, again, these would be products, these would be reactants, but now I switch reactants and products, so it's flipped. So HB over H0 plus B minus. Okay, I did that because I want to see what's going to happen when HA reacts with B minus. And from looks of things, it'll generate HB and A minus. If I look at this right, the H0 plus and the water are going to cancel. So you're going to end up with just the HA reacting with B minus and A minus formed along with HB. Okay, when I add reactions, I multiply their K equilibriums. So you add other values, you add delta G, delta H, delta S, but for K, we multiply. So if I multiply this by this, the 1 over, I'm going to find that K equilibrium is this times this, so this numerator, this denominator. And so plugging in, that would be this times this. So let's see what cancels. Hopefully something does. Oh, H0 plus canceled. Water isn't included. So we end up with A minus times HB. Ah, perfect. Those are the products. Divided by HA times B minus, the reactants. So sure enough, this is true. So we're going to take advantage of this relationship to make a prediction about what happens behavior-wise in this reaction. Okay, so we're doing math at this point. Eventually, I'm going to want to do conceptual aspect, but for math-wise, if I look at this relationship, the Ka, as mentioned, is 10 to the minus pKa, and this is 10 to the minus pKa. But when you divide, it's like multiplied by a positive. So this moves up and is now positive. And then when you multiply numbers, you add their exponents. When you divide numbers, you subtract their exponents. So pK of HA of 8B minus this, the negative sign is what's messing it up. So numerator stayed negative, denominator became positive. And so it ends up that HB, as I drew it with my product acid, so once again, it's a product minus reactant, but the K equilibrium for any reaction between one acid and the conjugate base of a different acid is going to basically be 10 to the pK product minus P, well, it's already written there. I don't know why I'm writing it again, but it's basically these two. Okay, it makes sense in that if this is a stronger acid, That means this is a weaker acid. So this would be the stronger conjugate base than the weaker conjugate base. Stronger reagents would go to weaker reagents. Conceptually speaking, you always want to go from stronger to weaker. Stronger reagents mean they're more reactive, less stable. Less reactive means more stable. So reactions always want to go to more stable products. So they will always go in the direction of that. So a stronger acid have a lower pK, weaker acid have a higher pK. So it's always going to go from the lower pK to the larger pK, which is why K equilibrium is favorable if it's 10 to a big number minus 10 to a small number. So it mathematically fits with the concept. It always should, but make sure that makes sense. So product minus reactant, that's what the math tells me. So if you trust the derivation, then I trust this final end result. But I also go with the stronger. Let's say this one's stronger, this one's weaker. Stronger will go to weaker. The lower pK acid is going to push to the higher pH acid every time. Okay, so now we're going to apply this. It may seem weird at first. Give it a second, see how it works. So let's say, for sake of argument, we're dealing with a carboxylic acid and a phenol again, the two acids I seem to throw at you a lot. So lower pK would make that the stronger acid. The higher pK would make that the weaker acid. If this acid is stronger, its conjugate base is weaker. If this acid is weaker, its conjugate base is stronger. So stronger reagents mean more reactive, weaker means less reactive or more stable. So it's going to go from more reactive to less reactive, or if you will, less stable to more stable. So again, reactivity is the opposite of stability. Stronger means more reactive is less stable, weaker means less reactive and more stable. Things want to go to the more stable side. So we predict K equilibrium to be greater than 1. If we did the math approach, product minus reactant, this would be pK of product acid, which is 10, minus pK of the reactant acid, which is 5. 10 minus 5 equals 5. 10 to the 5th is 100,000. That's pretty much bigger than 1. So this would favor the forward direction. So whether you want to do it by stability and strength and weak, like how strong and weak it is, how stable or unstable it is, that works. Or if you want to just plug in the math. Both methods work. And this is something academically you get to start making choices in the way you do things. There is more than one way to solve most problems. You need to find your best way. Okay, so we'll try it again. I'll use clever new acids instead of HA and HB. I've now creatively had HJ and HZ. I'm trying to pick letters that are not elements so that we don't mistakenly do that. So there's no reason why I picked the letters I chose other than just wanted to avoid any sort of misconception of it being a real molecule. So I'm going to make my numbers a little, I don't know, more realistic, have some decimal places. It's still going to be a small number minus a large number. So product minus reactant, 6.11 minus 8.43 is going to be negative 2.32. 10 to a negative number is unfavorable. So let's see how this works. So weaker acid, stronger acid. So conceptually speaking, the stronger the acid will have a weaker conjugate base. The weaker acid has a stronger conjugate base. Stronger, stronger. That's more reactive. Weaker, weaker, less reactive. Less reactive is more stable. More reactive is less stable. So it's going to go in the reverse direction. We predict K equilibrium is less than 1 based on the conceptual perspective. Mathematical perspective, we verify with 6.11 minus 8.43, which is 2 to the minus 2.32, which sure enough, negative number, 10 negative number is less than 1. The math works and the conceptual approach works. OChem, we are probably going to use conceptual more than anything else. We're not going to break out a calculator on a lot of things, but this is pretty straightforward in terms of math, product minus reactant, and in terms of concept. Okay, so compounds that you absolutely have to know the pKs for. Mentioned carboxylic acids, benzoic acid is 5, carboxylic acid is typically 3 to 5. Amines are basic when you protonate them, add an H plus to it. So I've shown what's called a primary amine, just one R group on the nitrogen. Their pKs are around 9 to 11. Phenol we mentioned earlier was around 10. Thiols, also mentioned those were acidic. They have a sulfur. They're roughly also around 10-ish. Acids, acids are acidic with OH there, but when OH has no carbonyl, and we see this in alcohol, then we can make them acidic, but this pK, if you remember, pK of water is coming around 14. So consequently, this is about the same, if not a little bit weaker than water. So we could only take an H off this if we added a really, really strong base in the absence of water, because if we add it to water, it'll react with water rather than this compound. But we still can. And then acetone or a ketone, the H on a carbon, it's not going to be terribly acidic. When you start getting up in the 20 range, that's just so weakly acidic. But this H, because of resonance, we deprotonate and go in here. That resonance helps it become somewhat acidic. Then we also mentioned alkynes are more acidic than alkenes, alkenes more than alkanes. So alkynes, I'm going to put 25, around 25. Reality is this molecule is actually 26, but that's in the ballpark. So I've chosen my numbers. The ranges are reasonable. The truth of the matter is, if you looked up numbers online versus a textbook versus another textbook, you would eventually find that no two sources give you the same numbers repeatedly. There's a handful, like water, we have to know because that's a definition. But because of this, I don't think it's worth memorizing exact numbers, but knowing rough numbers. And I'm definitely going to throw specific numbers as we go. My numbers are found by averaging a whole bunch of different sources, a few online, multiple textbooks, and coming up with a number that's kind of a hybrid of all of them. So I have no idea if my number is any better than anybody else's number, but gosh, it's so interesting. If I did just one book, it'd be plagiarism, but apparently because I did multiple books, I did research. So I researched these numbers and gave an average value for all of these. So any number you see here is exact for this, but if you go somewhere else, you might see a different number. So do not memorize exact numbers, no rough numbers. But here's the thing that'll help. If you can count by fives, 5, 10, 10, 10, 15, 20, 25. Those are what you should remember. So that's going to be close enough. They aren't precise. They're going to be off by 1 or 2. I'm going to be fine with that. You should be fine with that as well. But if you remember 5 to 10, 15, 20, 25, you're set. So 5 to 10, 15, 20, 25. So carboxylic acid is most acidic. The word acid is right there in the name. These are my 5. My to 10 are protonated amines, phenols, and thiols. And then you get to really weak ones. 15, 20, 25 would be alcohols, ketones, and alkynes. Okay, so 5 to 10, 15, 20, 25. Feeling pretty good about this. Also expect you to know that when it comes to bio versus OChem, things are a little bit different. So in OChem, I'm going to call it a 3 to 5. If you take biochem, you're going to learn the carboxyl terminal of amino acid, A standing for amino acid, is around 2 to 3 for most of the amino acids. Some will be slightly lower than 2. I think you can even get right up to 3 for one of them. So the moral to the story is, again, it's always a range. But for carboxylic acids in OChem, where it's just an R group, they're going to be 3 to 5. When you put an amine on there and protonate it, then it's going to end up pulling it down by something we're going to call the inductive effect. So if those are my pKs, then the pKb for the conjugate base will just be 14 minus these numbers. Okay, this is the physio form. pH of the cell is around 7.4, so 7.4 higher these numbers. So in the body, we see carboxylate. You talk about succinic acid, nope. You talk about succinate. You talk about, malonic acid, nope. You talk about malonate. Carboxylates, amino acids come as a deprotonated carboxyl terminal, but it's just important to know that carboxylic acids biologically are typically negative. On the other hand, the amines, the amino terminal is positive because their pKs are 9 to 10-ish, and 7 is less than this, so pH is less than pK, so things get protonated, so they exist in that form physiologically. Okay, so these are common organic compounds. Their pKs are 5 to 10, 15, 20, 25. And I'm set. I have 7 compounds. Carboxylic acid's the most acidic. Amine, protein-amines, phenols, and thiols. That's the 10, and then alcohols 15, ketones 20, alkynes 25. Okay, I have my memorization down, and I have my quality of life type questions where I look and make a decision on the quality of the compound, what it's going to do. Maybe quality of life, not but quality of reaction questions. So I'm going to do these qualitatively. So pK carboxylic acids around 5, thiols are around 10, products minus reactants. So if I want to do it math-wise, I would do pKa 5 and 10. So pK of product minus pK of reactant acid. And then keep in mind that's 10 to the power. So this would be 10 to the 10 minus 5, which equals 10 to the 5th, which would favor this. So K equilibrium much greater than 1. So it would favor that. Okay? So let me do it conceptually. Stronger acid, weaker acid. So that would mean this is the weaker conjugate base and stronger conjugate base. Again, stronger reagents are more reactive, weaker ones are less reactive. More reactive means less stable, less reactive means more stable. Things always want to go in the direction of more stable. K equilibrium is greater than 1. K equilibrium is around 10 to the 6, just like we just calculated. Okay, I said 10 to the 5, but apparently I'm calling the 11 here. So 11 minus 5 is 6, so around 10 to the 6. Okay, so far so good. Another compound. So this is one where I need to figure out what they're going to be. Alcohols, they're one of the 10s. Protein-amines are one of the 10s. So this is going to be really close to a perfectly balanced equilibrium. It's going to be barely in favor of one side or the other, depending on what numbers we give. Oh, I lied to you. I completely lied to you. My mistake. So this is alcohol, that's 15, this is my 10. So sincerely apologize on that one. Phenol, I was thinking phenol when I should have been thinking alcohol. Alcohol is around 15. I'm going to call it a 16 apparently. So roughly in the neighborhood, hence the rough number. So equilibrium wise, it would be 10 to the minus 10. I'm sorry, 10 to the 10 minus 16 or 10 to the minus 6, which means it's definitely going to favor that direction. So let's see how it works conceptually. Weaker acid has a higher pK, stronger acid has lower pK. Stronger acid goes to the weaker conjugate base. Weaker acid goes to the stronger conjugate base. Stronger reagents are less more reactive. Weaker reagents are less reactive. More reactive means less stable. Less reactive means more stable. Reactions go in the direction of more stable. It sure enough goes backwards as this number predicted. Okay, so again, my apologies. This was 16, not a 10. My sincere apologies. If I gave you one that was a phenol, then that'd be a really hard one. You have to know this number a little bit better and that number a little bit better to actually make a decision. Okay, so this was the one I was getting ahead of myself on. So phenols are one of the 10s, protein-amines one of the 10s, and thiols. So these are both roughly 10. So this is the one I was, again, last time getting ahead of myself. So this one, I need the numbers because they're both approximately 10. So it ends up, let's say we're dealing with phenol, that's like 9.95 for phenol. And let's say I'm dealing with methyl thiol, which is around 11.1 or 2. So it is a case then of 10 to the 11 minus 10, which equals 10 to the 1. So equilibrium is greater than 1. So it should favor products, but not that much. 10 is really not that much of a number. So basically this times this, divide this, and this equals 10. Square root of 10 is like 3 point something, 3.1-ish. So it's basically a ratio of 3.1, 3.1, 1, and 1. So about 3 to 1 ratio would give you this equilibrium. So it favors it, but only by about a 3 to 1 ratio. Okay. Again, same story. Lower pK, stronger acid, higher pK, weaker acid. Stronger acid has a weaker conjugate base. Weaker acid has a stronger conjugate base. Stronger reagents are more reactive. Weaker reagents are less reactive. More reactive is less stable. Less reactive, more stable. So it's going to go in the forward direction, as we already predicted number-wise. Okay, so you will undoubtedly have to be able to do this in homework questions, test questions, just predict which way an equilibrium lies, and that will ultimately help us just get in the right habit of looking at equilibrium for all our reactions. So that's why I like the more stable, less stable, even though the math seems a lot easier. When I deal with pKs, it honestly is probably easier to do it that way. But I want to get in the habit of considering the stronger, weaker reagents and the more stable, less stable perspective, because that's ultimately what I'm going to use down the road for other reactions. Okay, so now I have to determine if K equilibrium is greater than or less than 1. So alcohol and a carboxylate. So I don't know what those things are. So let me see if I can remember. Alcohols, I believe, are the ones that have an OH. Carboxylic acids also have an OH, but they're not asking for a carboxylic acid. They're asking for a carboxylate. So instead of the H, it's got a negative charge. Okay, so when it reacts, this negative is going to pick up that H. So my product side is going to be RCH2O minus, and then not necessarily same R. R simply stands for carbon chain. So those two and those two will be in equilibrium with that. So let me get rid of my drawing and put the rest in. So alcohol becomes an alkoxide, carboxylate becomes carboxylic acid. Those are the two things I just drew. Alcohol is a weaker acid, pK around 15-ish. Carboxylic acid is a pK around 5-ish. So stronger acid. So that means you're always going to go from stronger, the more reactive, to weaker, the more stable. So less stable to more stable. So K equilibrium is less than 1, and it ends up it's going to be around 10 to the minus 10. So it's going to be really favorable to go backwards. So if you add an alcohol and carboxylate, those two will not react. You would not see any detectable product without employing a very sensitive machine. Okay. Thiol and phenoxide. So again, I need to know my compound. So I believe a thiol is SH. Phenols are benzene ring with an OH. So just like before, it's asking for not phenol, but phenoxide. So I get rid of my H. And that's when I'm reacting. That will go then to one becoming H, one and losing an H. So my products will be RCH2S minus plus my phenol. So my product will be an alkyl sulfide and a phenol. So alkyl sulfide is kind of a loose name because if it's sulfur's got two R groups, we also call it that. So it's just our nomenclature does break down at times, but sulfide implying negative. So an alkyl sulfide anion is probably what I should call it. And then phenol. Okay, so I'm going to get rid of my drawings. I'm going to tell you the pKs are, these are my 10 one. This is the one that's going to be kind of tricky. So again, the thiol, depending on what it is going to be 10 or a little bit higher, 10 to 12. Phenoxide is going to be, or phenol is going to be around 10. So 10 as opposed to 10 to 12. So this one's going to be a little bit higher pKa. So the weaker acid, phenol is a stronger acid. So consequently, stronger acid would be more reactive. So weaker acid would be more stable. So stable on the reactant side, but barely. This is one of those I mix it together. 60% might stay here, 40% might form, or maybe 80%, 20%. It's not going to be a very significant amount that moves over. All righty. Draw a favorable reaction between ammonia and acetate. So these questions are getting harder and harder. The same concept, The same arrow, the same math. It's all easy once it's set up. It's the setting it up part. So let's start with ammonia. Ammonia is NH3. That is a base. So on the product side, it's going to be the conjugate acid, NH4 plus. And then acetate, ACE, if you recall, is that group. Sorry, I'm slanting up, but I just didn't plan my page as well as I could have. So those two are going to react. I'm going to transfer a proton. So when you look at this, as I'm doing this, this is going to work out. So now I got to figure out what the question is asking. So this cannot be possible. Why is that? Negative plus neutral cannot become positive plus neutral. So I need to flip either the acetate or the ammonia. So now let me go into the second part of this. Favorable means we're going from stronger to weaker. So the question is, which is a stronger acid? Amines, we say these are around 10, or carboxylic acids, which are around 5. So this one specifically is 4.74. So if that's the case, the stronger acid is this one. So this has to go to that side, and this has to go to that side. Okay, my mess, I'm going to get rid of it, and the computer's going to come in with a prettier picture. So I have to put it in a certain way. So again, ammonia, acetate, weak base, weak base. So that's not working out for me. Conjugate acid, conjugate acid. So you can't react a base and a base. You get an acid and acid. Neutral and negative cannot go on to form a positive and neutral, as we mentioned. So we have to flip things around. So because this is the stronger acid, it's got to go over here. Its conjugate then has to go there. And then the weaker acid has to go up here. And that has to go there. So that is how we have to set this up to make sure this is true. So let me just do the math. This is around 5. This is around 10. Ka equals 10 to the 10 minus 5, which equals 10 to the 5th, which is greater than 1, so it would be favorable as drawn. So I've double checked it, and I feel pretty good about this one. This is a tough question. So notice nomenclature and memorizing the pKa's brought it up to a next level in terms of questions. So one of the things you have to get used to is taking a simple thought and answering a simple question. And then once you know that simple question, make the question medium and using that thought plus an extra piece of information to solve the medium question. And then taking that same concept and that same definition and adding in a twist or an observation or some piece of information on top of the first one and putting it all together into a very challenging question. So little by little by little, we scaled up from just identify the number to now knowing what the number is supposed to be, identify which way the reaction goes, to now figure out what's going on from scratch. Okay, this was a tough one, but hopefully if you go through it slowly and try those questions individually, you will do quite well in them. So with that in mind, we have once again reached the end of another Toddcast. So I will see you at the next one. Bye.